Okay, so how many times did the odds win? What's the fraction out of 20 turn into a percent? So how many, raise your hand if the odds won. Raise your hand if the evens won. Raise your hand if it was super lopsided. Like a lot to a little. Okay? So maybe the odds just had a run of bad luck, right?
No.
Maybe. Okay? Or maybe not. So here's what we're going to do. Let's compile our group results. So how many groups we had? 1, 2, 3, 4. We had 5 groups. So what's the bottom of our fraction?
20.
We're going to compile.
100.
100.
Oh, then 100 times? No, we're adding our groups together.
We're compiling results. So for how many times did odds win for you?
5.
How many times did evens win?
15.
Okay, I'm just trying to make sure that we have the correct. I know it should be 20. So what about you guys?
6 and 14. 2 and 18.
Oof. Aye. Okay.
Oh.
Wow.
You.
Is that see, this is statistics.
That's,
Is that unlikely? Right?
are you lying?
9 and 11.
Okay, so let's do a little math here. 11, 12, 13, 23, 32. So this would be, and make sure my math is right here. So 29, 37, 47, 57, 68. So find the percent of rolls that were odd products for the whole class. So what's my percent? This actually works out really nicely for us, right? What's the percent? So it's 32 out of 100, which is 32%. How does it compare to your group results? Well, we can kind of see here, right? So that's pretty close to this one, pretty close to this one. I mean, it's higher than this one. And then here, mixed, okay? So is this just coincidence? Is the question. So what we are concerning ourselves with comparing to in this chapter is, here's what actually happened. You have some results. We have results as a class, right? What we want to compare to is what? The probability that this would happen. So what are we trying to find? So that's the comparison, right? Because Anika's group goes, well, we had 6. Is that weird? Well, what do we compare weird to? We compare weird to normal. Where do we get normal in this case? We're going to run a simulation. So what does our simulation look like? Look at number 4. This is our simulation. I want to complete the table below. And what we're going to do is, this is a pretty common thing to do in probability, is to use a table like this to simulate dice. So here's what we're going to do. We're going to say, what are all the possibilities? So before you roll the dice, what could have happened? And so here's what we're going to do. Imagine that this is one of the die and this is one of the die. So you do like 1 times 1. So this would be 1, right? 2, 3, 4, 5, 6, 2. So fill in the chart, please. Fill in the chart. Yes, it is a multiplication table. But we're using it as a simulation of dice probabilities. So now, this is every single possibility. Okay, this is every single possibility. What this is called in statistics, you ready? It's called the sample space. The sample space is every possibility. Sample spaces like this are easy to come by. What if it had been 3 dice, though? Would that be as easy to come by? No. Could you list out all the possibilities of 3 dice? Yes. You can always list the sample space. Sometimes it's harder than others. So now, what I'd like for you to do with your group here is to figure out the probability of actually rolling an odd product. What is it? Here's what I got. I found 9. 9 out of what? How many possible outcomes do we have?
36.
Okay, so we have 9 out of 36, and probability, express it as a fraction, then as a decimal. What is that?
1.25.
Is 25%. Look at that. Okay, so exactly what Madison and Ryan got. So they got 25%. And so we had another one that was close, another one that was lower, and 2 that were kind of off. But overall, how does our comparison happen? So which is closer to the percentage found in number 4, your group data or the classroom data? Why do you think that is? Answer this question for yourselves. I'm on number 5 right now.
Ours had a smaller sample. If you had a really, really big sample, it would have been closer.
Bingo. You got it. So let's imagine we didn't have somebody that got it. So ideally, what happens is the larger number of rolls, the closer class data becomes to probability. Okay? So the larger the class data becomes to probability. What did we call this last time? You remember? This is the law of large numbers. As more trials happen, the empirical probability gets closer to the theoretical probability. Remember that? Yeah.
And like, say we do a test, and it's like, can we use that law of large numbers as
Yes.
an example of? Okay.
Yeah, so in theory, so yours was right on. So in that case, it actually got farther away as we compiled the class data, but in general, a smaller sample size is going to yield less consistent results to actual probability, or less consistent results to theoretical probability. Okay, I'd like for you to complete number 6, A, B, and C. So what you're going to do is you're going to use the table to find the probability of rolling each of the following products. Yeah.
Number besides 6? Does that mean any number but 6?
Use the table to find the probability of rolling each of the following products. What about a 4 or a 5? How many ways are there to roll a 4 or a 5? How many ways are there to roll a 4? I erased my chart. There's 3 ways to roll a 4. What about 5?
2.
Okay. So what do we do with those?
Add.
You got to add them. There are 5 ways out of 36 to roll a 4 or a 5. What about a number besides 6?
32.
How'd you do that?
Sounds
So what you did was you said there's 36 out of 36 ways to roll the dice, and I'm going to take away the ways that there are to roll a 6, which was 4 out of 36. So I get 32 out of 36. Here's an important note on probability. You ready? Leave it. Leave it. Leave it. Why is that important? What does it tell you? the number of possible outcomes. Okay. What about the probability that the number you roll is between 1 and 36? Okay, little preview here. This, or in probability, means add. Okay? Or means add. You're adding probabilities together. We're going to study this a little bit more in just a minute. The word besides is called the complement rule. Not like, hey, you look nice today. That's not the compliment that I'm talking about. I'm talking about the complement, meaning the event that goes with it. Okay? The event that goes with it. Complement is done by taking all the outcomes and subtracting the opposite event. So a number besides 6, you could count up those 32, or you could just say, what are the ways to roll 6 subtracted? This one, all outcomes must add to 1. The probability of all outcomes must add to 1. Meaning you add them all up, the probability of any event happening will be 1. Does that make sense? You guys with me? I think you're pretty. No?
I don't understand the last one. What is that?
Probability must add to 1. So there's a 3 in 36 chance of rolling a 4. There's a 2 in 36 chance of rolling a 5. Well, if I had a probability of rolling any number, all of them together would add up to 1 because there's a 100% probability that anything happens. Let's talk about a couple of important ideas. You guys have a pretty good handle on this. Probability models. We actually did this last time, right? We were trying to find a way to model certain situations using dice or coins or cards. Probability model is a list showing all outcomes possible and their probabilities. Okay, so a probability model is a list of all possible outcomes and their probabilities. I'm going to draw a big arrow. I want to encourage you to do that too. You ready? This right down below here, so peek down. So down this chart at the bottom here, where it talks about the color of the M&Ms and the probability of the M&Ms coming up, that's a probability model. It's pretty cool because it lays out every possible outcome, but unlike the sample space that we discussed, it lists the probability of that event happening. So if you'll notice, all those probabilities add to 1. So in the probability model, all the probabilities must add to 1. And each probability is between 0 and 1. They list them in decimal form. Between 0 and 1, all of them add up to 1. You can't exclude an outcome. Complement is the probability of an event not happening. It's the probability of an event not happening. You guys familiar with cards? Anybody here a card player? Play cards with your grandma? I always play cards with my grandma. How many kings are there in a deck?
4.
Okay. How many cards are there in a deck?
52. It's 52, right?
52. How many cards are there in a deck that aren't kings?
48.
48. 52 minus 4. So if I say what's the probability, so what's the number of cards that aren't kings? You're like, you just subtract, that's silly. Yeah, that's complement. The complement is taking everything that's possible and subtracting what's not what you want. So the complementary event is the opposite event of what you want to happen. Okay? So if there's a 30% chance of rain today, what's the percent chance of not raining? 70, right?
8% it maybe won't.
Oh,
Good. I saved it.
Okay, here's a lot of letters. Probability of A superscript C is equal to 1 minus P A. I'm going to tell you what those letters mean in just a minute here. This P right here means probability of. So whenever you see a P with parentheses, it's probability of. So if, take these two things together, I'm adding a little note on the side here. So P, so P roll a 4 means probability of rolling a 4. Does that make sense? That's just notation. That's probability notation. A superscript C is complement of A, meaning event A. What's the complement of rolling a 4? Not rolling a 4. Not rolling a 4. I didn't put parameters on this. Are you rolling 2 dice or are you rolling 1 die? What is it? Okay. So the complement of rolling a 4 would be not rolling a 4. So now if I said, what we're going to do is we're going to roll this die. The event that we're measuring, event A, is rolling a 4. What's the complement of rolling a 4 with 1 die?
5 over 6.
The probability would be 5 over 6, right? It'd be 1, 2, 3, 5, or 6. Does that make sense? So event, complement of events. Okay.
wait, so wouldn't it, like you said probability of rolling a 4, but wouldn't it be like probability of not rolling a 4?
Yeah. Yeah.
Okay.
That's what this means here. This all goes together. So P parentheses roll a 4 means probability of rolling a 4.
Okay.
Okay. What does it mean to be mutually exclusive?
I'm not connected.
How so?
Like one event doesn't affect the next one.
Yes.
What's between like the A, C, and
A is the complement of A. A is just A. A capital letter in probability just stands for an event. So in this case, I could say event A is rolling a 4.
So then you do not roll a 4 in the first one.
Would be the complement.
So would you write in that not rolling a 4? Or would you write rolling a 4?
You could write not a 4. Probability not a 4. Mutually exclusive events are events that cannot happen together. Okay, mutually exclusive events are events that cannot happen together. For example, probability of being in dress code while at the same time being out of dress code. They are mutually exclusive. Either you are in or you are out. And here's the general addition rule. Honestly, we already did this, but it's the notation. The probability of A or B is written like this. You ready? About to go all symbols on you. This is not a U. It's a union symbol. Bless you. So the probability of A or B is equal to the probability of A union B. It's a big upside down U, but it doesn't have the tail. Which is equal to the probability of A plus the probability of B. Okay? All right. I want you to work through this, check your understanding. It doesn't use fractions. Sometimes people get a little bit uneasy when fractions start to pop up in these probabilities. But remember, you can always convert to decimals. This one includes decimals. This is a probability model down here. So it must respect the rules of probability models, meaning it's got to have the outcome with the probability listed. They have to be between 0 and 1. They all have to add to 1. So work through the problem down there and figure out some of these probabilities as they are associated with, as my daughter calls them, M&Ms. So let's chat here for just a minute. One important thing about experimental design and understanding probability problems is understanding exactly what you're doing. What are we doing in this simulation?
It's a random M&M out the bag.
How many?
One.
You one random M&M. So think about that. And one of the things that helps me sometimes when I'm doing probability problems is to think about what I'm actually doing, like picture myself doing it. I know that seems silly. But if I imagine myself reaching into a bag of M&Ms and pulling one out, is there a probability or possibility that it's two colors? No. If I eat that one and I reach into the bag for the next one, does the color that I picked the time before have any bearing on what the next color is? No. So these are independent events. That's very important to remember, like exactly what's going on when you're doing these simulations and when you're talking about these things. So here's the probability model, right?
I have a question.
Yes.
Is that independent because doesn't the total number
Yeah, you
decrease?
took one out, so all
Isn't
the
that-
probabilities change.
So yeah, like
Like if you put it back in, then they're independent. But if
Yeah.
you like leave it, if you ate it, then they're dependent.
What is this set of numbers measuring?
And independent probability
Of what?
of picking out one of them if you
Oh,
leave all of
of
them.
all the
in.
outcomes.
Like of each time.
How do they determine these probabilities? Was it based on that bag? Or was it based on the population of M&Ms that Mars has ever produced?
Population.
Well,
It
I
doesn't say.
Read the prompt. Suppose you tear open the bag of M&Ms, pour one candy into your hand, and observe the color. According to Mars Incorporated, the maker of M&Ms, the probability model for a bag of a bag from its Cleveland factory is.
So
So it's like an average. It's a population.
This is the ratios that they put into producing M&Ms. So when it goes into the bag, it has this ratio,
Why don't they
in
just
theory.
make it equal? Yeah, why did
Let's blow your mind even further. Different plants have different ratios of colors that they put out. But why though? I don't know. I have no idea. What's that? I have no idea. I don't know. But what they've determined is that 20% are blue, 20% are orange, 20% are green, about 13% yellow, 13% red, and 12% brown. For whatever reason, they've determined that this is the ratio from this plant that comes out. So when you have this bag of M&Ms, yes, if I measure the empirical probability, meaning I sort out the bag, I figure out the ratios, we could measure that versus this, right? But if I don't have a probability model that's for that bag, does an event pulling one out change the probability of getting a green in this bag? No, it doesn't. No, because this probability model has to do with M&Ms overall, not this bag. Okay? Explain why this is a valid probability model. There's two reasons. One is what?
They add up.
One. They add up to 1. So the probabilities add up to 1. What's the second part?
All go between 0 and 1.
That's all possible outcomes. And the probabilities.
Lists all possible outcomes. And you could say 3. They are between 0 and 1. Yes, those things. All those things. True. Make it a valid probability model. Explain why events red and blue are mutually exclusive. Lay it on me. Why are those mutually exclusive?
Because you're picking one, so it can't be
Yeah, you pick one. It can't be 2 colors. Moving on.
Oh my god.
Find each of the following events using proper notation and write the probabilities. So, you've probably got the number right, but let's review the notation as well. Find the probability that you don't get a blue M&M. How did you write that? How did you do notation on that?
You
1 minus.
subtract the blue
So-
from 1.
1 minus the probability of blue, like that?
Yes.
Not exactly.
You just do 1 minus 0.207.
That is going to.
There are 2 ways to write this. 1 minus the probability of getting a blue, right? You agree? Or not? Yeah, so if I know the probability of getting a blue is 0.207, you could do 1 minus 0.207, which was what?
0.793.
Did you get the number part right?
Yeah.
Yeah. Or probability of blue complement, what else could you do?
Add everything up.
Add up all the other ones. But what answer did you get when you did that? 0.793. Believe me when I say this to you. You need to understand this notation. Okay? Understand the notation.
Wait,
So,
do we have to write exactly 1 minus p
Yeah.
Yeah.
parentheses?
That
Whatever.
confuses my brain.
So yes.
Okay.
this is proper notation. So this is understanding what the question is asking sometimes. So P means probability. Whatever's inside the parentheses, you can write that a bunch of different ways. In this case, they did BL, like BLC. Okay, blue complement. But a superscript of C means complement. What's the probability that you get an orange or a brown?
0.3 is not.
So let's talk about notation first. How would you write this?
P
P
of
parentheses.
OR.
No,
OR
1
union
minus.
BR.
P of orange
Plus.
plus P of brown. What else could you write?
1
1
minus.
minus
P,
orange plus brown. Or 1 minus
P-
the opposite of orange.
No, because you want
what about this? P orange,
to the union sign.
union, brown. Maybe you did an O and a B, R, that'd be okay.
Wait, what is union?
It means or. This literally means or, this union symbol. Okay, so no matter how you slice it, let's put it like this. P of orange, union, brown equals P of orange, so probability of orange plus probability of brown is equal to, and you should write this out, 0.205 plus 0.124 equals 0.329. Write out the pieces. Da, 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 da. What's the probability that you don't get a red or a green? This one's tricky. Check this out. There's a couple ways to write it. What do you think about this? Sprung it on him.
No, you can't do that.
I can and I will. Yes, you can.
One
You
minus.
can't?
Yes, you can.
Once
So,
you do the one minus b.
so there's some other ways to write it, right? So you could do 1 minus the probability of things, but this is proper notation for this. The complement of red or green. Do you agree? It's the complement of red or green. So,
We kind of wrong to the 1 minus b.
so hold on. The probability of the complement of red or the complement of green equals 1 minus what?
Complement the R.
No, p
No.
r plus
P red.
p g.
What do you think about that? 1 minus the probability of R plus the probability of G? Well, it should look like this. So you'd have 1 minus 0.131 minus 0.198 is equal to 0.671. Here's what I'm fully confident of. Maybe overly so, but I don't think so. I'm sure you understand this part and this part and this part. I think the notation's probably where you're like, I don't know. Right? Especially on this one. What's the probability that you don't get a red or a green? Oh, I just add up the ones that aren't red or green. Exactly. But what I'm trying to get you to do is this. You can get that answer, but understand where the complement comes in. Because what's going to happen is you're going to have events that you don't know the probability of the complements in order to add them. You're only going to know the probability of a given event. And you're going to have to discern what the probability of the complementary event is. Does that make sense? For example, the probability that you get malaria is 1.6%. What's the probability that you don't get malaria?
9.8.
Okay, so it'd be a 1 minus. So I need you to sort of conceptually understand this 1 minus, the concept of 1 minus. Does that make sense? Okay, let's do an experiment. We're gonna do an experiment. Now, you're not allowed to practice for this experiment, okay? If you practice, it doesn't work. And you have to be honest. This is not a judgment of you. But we just need to know. Can you taco tongue and evil eyebrow?
What's taco?
Taco tongue is this.
It's like the. Oh.
Where you roll your tongue into a
Like,
taco.
can you 3-leaf clover? No, this 3-1, right?
Right?
No, we
So-
talked about it to see the
So we need to know. So we're gonna try to answer the question. Is this genetic? And we're not really gonna answer that question, but some people believe that that's true. So no amount of practicing over the years can help you do it. You just can or you can't. Can you taco tongue or evil eyebrow? You need to be honest about this. So we need to collect the class data to fill in the following. So we need to know some things. All right. I need to see your evil eyebrow.
What's the evil eye?
So can you raise one?
I feel weird doing that.
I don't
Why?
know if I can
Don't-
do that.
Don't feel weird.
I can do that.
You're not
You
gonna do
can't.
it. Both of mine go up.
Okay. All right. So we need to know. We need to know if you can do
You
it.
did it. You kind of did it.
I know I can't. I do that. It's like the only thing I can do.
I just look like
Ew,
All right. So let's see.
Yeah,
Who,
I
can you
can
evil
do
eye?
it.
So figure out your table. Who can evil eyebrow?
I
Who
felt
can't?
good. I felt good. When my eyebrows
So we got 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 people. So
I don't know. I can try eyebrow, but I think
One of them goes out there.
Wait,
I feel like here we go.
yeah.
Oh, one? Yeah.
All right.
The other one down.
So here's what we need to know. So now taco tongue. Do the taco tongue. Who can do it? Can you do it? You can do it.
Like, all three of them can.
Can you do it? Can you do it? So we need to try to fill in this chart. So how many of you can yes evil eyebrow and yes taco tongue? You can do both.
Oh no.
No, we all suck.
Really? Can you?
No.
It's only me? Wow. Okay.
Supposed to be
So how many of you can taco tongue but not evil eyebrow? 1, 2, 3, 4, 5. Wait, hold them up high. 1, 2, 3, 4, 5, 6, 7.
You can do it.
How many of you can evil eyebrow but you can't taco tongue?
0.
Yeah, I can't do it.
It's fine.
Oh wait, I can do the eyebrow but not the tongue.
Eyebrow but not the tongue.
Oh,
I
really?
could, but
Interesting. Okay.
You're not-
So how many of you you're like, I can't do either one? How many of you are like, I can't do either one?
Fine.
Okay.
Ew.
Right.
This is good. Okay. So this is good. So now what we're gonna do over here, does yours have this chart? Oh, it messed up. We actually want to draw a Venn diagram over here. We need to draw a Venn diagram. And what we're going to do is we're going to have two big circles like yay. And this is going to be...
Does it matter where the lines fall on the circle?
Yes. Wait, no, the lines are irrelevant.
Okay.
So the left circle is going to be yes, taco tongue. The right circle is going to be yes, evil eyebrow. And obviously, as you know, in the middle goes what's shared. Let's fill in a couple things here. All right, so let's check this out. Let's make some totals. We're making a two-way table here. So the total across would be 8 people total can do the taco tongue. 2 people cannot. And then, wait, that's not right. Somebody didn't weigh in.
No, we don't.
No, I know, but we have 11 people
Who's the cheater?
who didn't weigh in.
Madison.
I know I did. I said I
Okay, how many of you can taco tongue and evil eyebrow? You can do both. I'm the only one. Well, we gotta go together. So how many of you can do the taco tongue but not the evil eyebrow? You can taco tongue but not evil eyebrow? So you can do this,
Show me your taco tongue.
but not this.
That is not a taco tongue.
Well, yeah, I'm
Show us. Show us.
How many of you?
Show us the taco tongue.
You can't. I don't think you couldn't do it, right?
This is your try.
So Jack is no evil eyebrow. So Jack, can you do the evil eyebrow?
You can.
There it is. Okay. So Jack is here. So okay. So raise your hand for yes taco tongue but no evil eyebrow. 1, 2, 3, 4, 5, 6, 7, 8. Okay. There it is. Okay.
If I was not.
So then, is that everybody then?
Yes.
Okay, we got 11 and 11. Okay, perfect. So now, so where do these pieces go? So let's just think for a second. What goes in the middle? Which of the numbers? 1, right? Because one person can do both. So we're going to draw ourselves an arrow. This top left corner of our two-way table is going to go in the middle. It's shared. Can do both. What goes in this Pac-Man over here? The left Pac-Man, the yes taco tongue.
Only
The
taco
8
tongue.
people.
The 8 people.
Oh, JK,
Okay. So the 8 people can yes taco tongue, but they can't do the evil eyebrow. Does that make sense? What goes in the right Pac-Man?
sorry.
1. Where does it come from?
Yes, evil eyebrow.
The second. Well,
Yes, evil eyebrow.
Okay. And I'm gonna be outside all three circles.
Okay, and so this loner Dottie, the rebel, goes over here, right? There's one person who's outside of both of them. Okay, so now, this is how it goes. Okay, this is how it goes. When we make a two-way table, what is shared, so you put your two positive events, right? So you put your two positive events, your two negative events. Your top left corner is going to go into the shared. The diagonal goes into the Pac-Mans. The bottom right goes into the outside because the bottom right is excluded from both. I want you to pop down here and with your groups start to talk about number 2. So talk about what it means. So for example, probability, yes, taco tongue. Make it a probability. So I want you to list it as a fraction. So fill in number 2 with your groups. We're going to check in just a minute here. All right, let's chat. So what is the probability of yes to the taco tongue?
9/11.
9/11? Okay. What about the probability of no taco tongue?
2/11.
Don't those go together?
11 out, but I can't.
Complementary events, right? So together they should add up to, do they? Yes. Probability of yes, taco tongue, and yes, evil eyebrow. Probability yes to taco tongue and no evil eyebrow. 8 out of 11?
Yeah.
Do those two go together? They're next to each other, but they don't go together. What about the probability of yes, evil eyebrow?
2/11.
Okay. So what do you know about the second one? What would you call it?
9/11.
It's the complementary event, right? So it's either yes or no for this case. Probability of yes, evil eyebrow, and no taco tongue.
1/11.
What about the probability of no taco tongue and no evil eyebrow?
1/11.
The lone wolf. Okay. So let's suppose that we randomly choose a student from the class. Randomly choose a student from the class. Find the following probabilities. What's the probability of yes, evil eyebrow if we pick randomly from the class?
2/11.
Can we do RNG?
What?
Do we have to do RNG?
No.
It's 2/11.
Where do we get these probabilities now?
On top.
From the chart. We're going to get them from the chart. So now, the only probability frame of reference that we have is we are picking from this class. There's no precedent for this. This is just what it is. So what is the probability of a person saying yes to evil eyebrow? How many people could do it?
Isn't number 2 and number 3 the same?
Yeah.
What about probability of no evil eyebrow?
9/11.
So what's the probability of yes, evil eyebrow or no evil eyebrow?
11 out.
Why even go through that? Well, my point was to say these right here are mutually exclusive events. Those are mutually exclusive events. So either you can or you cannot. Okay? Either you can or you cannot. Let's look at the bottom. Suppose that we randomly choose a student from the class. Find the following probabilities. What's the probability of yes to taco tongue?
9/11.
Probability of yes to taco tongue. 9/11. Probability of yes to evil eyebrow.
Wait, evil eyebrow?
Isn't this the same thing we just did?
No, they're not compliments.
Just wait. What's the probability of yes, evil eyebrow? You just hit the nail on the head. They appear to be complements. Are they related? No. Okay. So when I say yes, probability of yes, taco tongue, or yes, evil eyebrow, what do we do? Why?
I have other.
Okay. So here we go. So the probability of yes, taco tongue,
Oh, who can't do it?
plus
Oh.
the probability of yes, evil eyebrow, minus what?
Repetition.
Where does the repetition come?
You.
It's me. It's me. You got to take one back. Because I've been counted twice in this. I was counted in yes, taco tongue. I was also counted in yes, evil eyebrow. So I got to take back the shared. What is shared? And so this would be 10 out of 11. The notation for this is probability of A plus probability of B minus the probability of A intersect B. Sorry, we're not there yet. Of A and B. How do we know this though? Well, think about it like this. These are not mutually exclusive. And honestly though, look back to the previous example, because this is where people are usually like, follow, 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 and now I'm lost. Who's shared? So think back to the exclusive events. Probability of yes, evil eyebrow. What was it? The very previous one. 2 over 11. What was the probability of no evil eyebrow? What's the probability that you could do both?
1, like 11 or 11.
You can't do both.
You can't do both of those.
Oh.
You can't do no evil eyebrow and evil eyebrow. So if you think about it like this, probability of the first event plus the probability of the second event minus the shared, what's shared in the one before?
All of them.
Nothing. There's no one that can do both of those. This is a formula, but you have understanding of this, right? So the probability of A or B happening is the probability of A plus the probability of B plus the probability, minus the probability of someone who happens to have both. It's true for both of these, but let's talk about it in terms of Venn diagrams. You ready? Two-way tables. And Venn diagrams. This will be a review of what we did. So this is a two-way table here. And here's what we're going to do. We have two events. In this case, it was taco tongue and evil eyebrow. Event A goes here. Event B goes here. The complement of B goes here. The complement of A goes here. 4 things happen. You get 4 numbers, right? As it relates to a Venn diagram, as long as you put your Venn diagram together like this, sorry, your two-way table, here's the A circle and the B circle. What is shared by both of them goes in the middle. What is in A but not in B goes in the left Pac-Man. What goes in B but is not shared by A goes in the right Pac-Man. And then there's everybody else on the outside. Here comes our general addition rule. We've already kind of outlined it, but I want to very easily put it down for you. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. If A and B are mutually exclusive, the probability of A and B is 0. Since they can't happen at the same time. That's the implication. If they're mutually exclusive, they can't happen at the same time. So that would mean the probability of A or B would be the probability of A plus the probability of B. Does that make sense? So what I'm telling you is the formula is exactly the same for mutually exclusive events or non-mutually exclusive events. But in mutually exclusive events, the probability of A and B happening at the same time is 0. So you subtract 0. You need to work an example of this. Go ahead and work on the check your understanding down here. And then we're going to go through it. The prompt is, what's the relationship between educational achievement and home ownership? A random sample of 500 U.S. adults was selected. Each member of the sample was identified as a high school graduate or not, and a homeowner or not. The two-way table displays the data. Suppose we chose a member of the sample at random. Define these events. G person is a high school graduate. H is a homeowner. I want to put a quick note on this. When you go to do this and describe a problem on the AP exam, you must label which event is which. Even if G and H are the most logical only choices that a person would possibly make, you gotta lay it out. You gotta say, this is what event is what. So, as we look at this, something that I like to do, I like to make my total columns. Did you do that? So I like to put my total columns right away. So like I put 310 here. I put 190 here. I totaled these across as 340. I totaled these across as 160. The reason I do that is because they said 500. I wanted to make sure everything added up to 500. So things should add to 500 both ways. So 500 is my total. That's a reminder to me. Explain in plain language what P parentheses G superscript C means and find the probability. You tell me. What does this symbology mean?
Probability of the person selected to not be a high school graduate.
probability that the person selected is not a high school graduate. So then they want us to find that probability. What you should write is P G superscript C is equal to, what is it? Which of the numbers is it? I see not a high school graduate. 190. That's all the people who are not high school graduates out of what? 500 is equal to what? 0.3. Must have this, must have this, must have this. Need to put all three things down. Why? Well, I don't know, if you're like me, you can't really do 190 divided by 500 in your head in a meaningful way. Oh, you have a 190 out of 500 chance of this happening. Is that good? You have a 38% chance of this happening. Is that good? Okay, it's more meaningful to put this, but you should show where it came from. Explain why P, G, or H is not equal to P of G plus P of H. What do you think? Why isn't that equal to it?
Not all homeowners are high school graduates.
Because they're mutually exclusive.
There are some people who graduated and had a home, right? So some people who fall into both categories. So what do we need to add in here? Minus P and G. You gotta subtract what's shared, because this means the probability that you graduated or you owned a home, and they're saying, oh, that equals the probability that you graduated and plus the probability that you owned a home. Well, I graduated and I own a home. I would be subtracted from this because I would have been counted in here and here. So there are some.
Can you just say like, because P of G and P of H are not mutually exclusive?
Yep. Yes. These are not mutually exclusive. They're not mutually exclusive events. So the probability of G or H should be the probability of G plus the probability of H minus the probability of G and H, which is equal to what? 310. Give me the whole deal. 310 over 500, because that's the probability of G, right? Plus the probability of H. What's that? 340 over 500 minus what?
221 over 500.
Yeah, so here's the shared, right? That's what goes in the middle of your Venn diagram. So minus those 221 people who got counted twice. So these 221, check it out. I mean, if you're struggling to figure out where this came from, I understand. But if I use this 340 number, it's the sum of this and this, right? But then in my 310 number, I use this and this. I can't use this twice. That make sense? So I should add this, but in adding my columns, I would have added that twice. So over 500, so what do I get here?
0.62.
429 over 500 equal to 0.858.
Oh, the 558?
So our Venn diagram. Let me scroll up. Venn diagram should be pretty similar to what we've done in the last two examples, meaning from the notes and also from that taco tongue / evil eyebrow. We're going to revisit this on Monday with our friends, or Tuesday. When they come back, we're going to talk about it. Something very important to do. If you put a Venn diagram, you must label G, H. So, where'd you put your numbers? What'd you put in the middle? What'd you put in your left Pac-Man?
89.
What'd you put in your right Pac-Man?
119.
What'd you put in the outside?
71.
Yup.
Wait, I thought the right goes to
Does it matter which side it's on?
the. Yeah, I think so.
It does.
Oh,
No,
wait,
as long as you
G?
label right.
As if you put H over here and G over here, so the 119 has to go with the H.
Do we have to put H and G, or can we put homeowner and grant?
You can put that.
Okay.
You just need to clearly identify it.
Yeah, okay.
So write the event is not a high school graduate and is a homeowner using notation. Symbolic form. What'd you put?
I put the G to the C and H.
That is correct. So is not a high school graduate, so that's G sub C or G superscript C, and is a homeowner. So that would be, look at your Venn diagram. They are a homeowner and not a high school graduate.
190.
So they're in this circle, but they don't overlap. So that would be 119 out of 500, which is equal to 0.238. Okay? Oh, darn. We ran out of time for the quiz.